Common sense dictates that an airplane must be stable. I released the steering wheel, it leveled itself and continued to fly smoothly. This is how most passenger aircraft are designed. But many modern fighters are designed in exactly the opposite way. They are aerodynamically unstable. On purpose. This is called relaxed static stability. And it sounds like a paradox. Why make a combat aircraft less stable? The answer is agility. A stable airplane resists changing its position in space. This is good for comfortable flight, but bad for quickly changing direction in a dogfight. Such an aircraft has to literally push each maneuvering action through the natural resistance of its own aerodynamics. An unstable aircraft, on the contrary, reacts to the slightest deviation of the rudders instantly and with minimal effort. He wants to change the trajectory under any influence. For a fighter pilot, this means the ability to perform sharper, faster maneuvers with the same amount of stick force. But there is an obvious problem. An unstable airplane, left to its own devices, does not fly smoothly. It begins to oscillate, deviate, and without constant correction, it loses control within seconds. A person is physically unable to make the necessary adjustments frequently and accurately by hand. The solution is a fly-by-wire control system. The computer receives signals from the aircraft's position sensors hundreds of times per second and automatically makes micro-adjustments through the control surfaces faster than a person can do. The pilot controls the plane not directly, but through this computer. He sets the desired action, and the computer decides how to physically implement it, while compensating for natural instability. The F-16 was one of the first production fighters built on this principle. So unstable that if the fly-by-wire control system completely fails, the plane becomes practically uncontrollable manually. The loss of the flight control system on the F-16 is almost guaranteed to mean disaster. This is a compromise that the engineers made deliberately. Maximum maneuverability in exchange for complete dependence on electronics. That is why modern fighters use multiple backup control channels, usually 4 independent computers voting among themselves so that the failure of one does not lead to loss of control. Instability tamed by a computer is the formula for modern air combat. If you look at archival recordings of air battles, a fighter almost never flies alone. Always a couple. Leader and follower. This is not an accident or a tradition. This is the result of decades of analysis of combat losses. The idea was born during the Second World War. German ace pilot Werner Mulders was one of the first to formulate the tactics of a pair rot instead of the then usual formation of 3 aircraft. The logic is simple, and that makes it brilliant. It is physically impossible for one pilot in a dogfight to simultaneously monitor the target in front and the threat behind. Human vision does not work 360 degrees at the same time. While you are aiming, your dead zone behind is open to attack. The couple solves this by dividing tasks. The leader focuses on attacking the target. The wingman covers the rear hemisphere, monitors threats, and warns of danger. Roles may change depending on the situation, but at every moment someone holds the perimeter. Modern tactics have developed this idea. Double attack formation. A double attack, when a pair splits into 2 single fighters attacking the target from different directions simultaneously, but maintaining visual and radar contact with each other. The enemy cannot simultaneously respond to 2 threats from different vectors. Using AWACS and data exchange systems, a pair today can operate at a distance of tens of kilometers from each other, remaining tactically united. Information about each other's position is transmitted automatically through a secure communication channel, a tactical data exchange system. Statistics of air battles in Vietnam showed a simple thing. Single aircraft that lost a wingman or were separated from a pair died many times more often. That is why one of the first rules of air combat that is hammered into a cadet's head is never lose a wingman. There is safety in numbers. In the sky, this rule works literally. The pilot of an Apache AX-64 helicopter wears a device that looks like something out of a science fiction movie. Monoscopic display fixed in front of one eye. The system is called EHAD's Integrated Helmet and Display Sighting System. But the most surprising thing is not the display. And what happens to the helicopter's gun? The 30mm M230 cannon, its zero, is located in the Apache's bow turret. It can turn in a wide sector forward, to the sides, down. It is not controlled by a joystick. It is controlled by the pilot's gaze. Special sensors track the position of the pilot's head with high accuracy. Where the pilot looks, the gun turns there. The pilot notices a target on the ground, turns his head, the turret follows the direction of his gaze in a fraction of a second. He pulls the trigger and the cannon fires exactly where the pilot was just looking. This fundamentally changes the reaction speed in battle. Previously, the pilot or gunner had to visually locate the target, then manually adjust the sights using the control stick, then fire. Now he found it, looked, and fired. One continuous sequence. The problem is the same as on fighter aircraft: signal delay and calibration accuracy. The slightest discrepancy between the real position of the head and what the system records, and the gun misses the target by tens of meters at the firing distance. There is also a physiological complexity. Constantly keeping one eye on the display and the other on the real world creates a special type of stress on the visual system. Apache pilots go through a special adaptation, some require months, for their brains to become comfortable processing this bifurcated visual information. Look-to-weapon technology is a harbinger of what will come to fighter aircraft in the coming years in an even more developed form. Apache has been flying for many years with a solution that the rest of military aviation is just beginning to truly embrace. Look closely at F-22 or F-35. Engine air intakes are not the simple round openings you might expect. They have a complex angular shape, hidden S-shaped channels, and an unusual arrangement. This is not an aesthetic decision. This is one of the most difficult engineering problems in aircraft manufacturing. The engine needs a smooth, undistorted airflow to operate efficiently. The slightest turbulence at the compressor inlet and efficiency drops, surging is possible. But at the same time, the air intake is one of the main sources of radar reflection of the aircraft. Why? Because inside the air intake there are engine compressor blades, metal, rotating, ideally reflecting radio waves back to the source. The radar sees the inside of the engine through the air intake as if through an open pipe with a mirror inside. The solution is an S-shaped channel. The air intake bends inside the fuselage so that there is no direct line of sight to the compressor blades from the outside. A radio wave entering the air intake is reflected from the walls of the channel several times, losing energy, before reaching the compressor and returning back. Part of the wave is absorbed by a special radio-absorbing coating inside the channel. But the bending of the channel creates another problem: loss of air pressure and its unevenness at the inlet to the engine. Engineers are forced to balance between aerodynamic efficiency and radar stealth, and almost always this is a trade-off not in favor of pure aerodynamics. There is one more detail: DSI, diverterless supersonic inlet, a diverterless supersonic air intake used on the EF-35. Traditional air intakes have a special slot, a diverter duct, that diverts the slow, turbulent boundary layer of air away from the fuselage, keeping it out of the engine. This works, but adds extra reflective surface and weight. DSA solves the problem with a special convex shape of the fairing in front of the air intake. The boundary layer air simply flows around this convexity and does not get inside, without the need for a mechanical diverter. Fewer parts, less weight, less radar signature. The shape of the air intake is a frozen compromise between the physics of gas flows and the physics of electromagnetic waves. Two opposing sciences that engineers are forced to reconcile in one detail. It seems obvious that camouflage is needed to make the plane less noticeable. But why then dozens of different paint schemes for the same type of aircraft, depending on the squadron, theater of operations, and even the specific mission? The answer is that visual camouflage in aviation solves different problems at different distances and altitudes. The air-to-air scheme, such as the gray two-tone paint scheme of most modern fighters, is designed to camouflage against the sky when viewed from below or from the side at medium to long ranges. The gray tone is chosen to blend with the typical color of a hazy sky at an altitude of several thousand meters. This is critical in maneuverable air combat, or a split second of visual detection of the enemy counts. The air-to-ground pattern, often darker, with green or brown spots, is designed to camouflage attack aircraft and helicopters when viewed from above, from the perspective of an observer on the ground or another aircraft. A-10 traditionally carries just such a scheme. There are also less obvious solutions. False cockpit lights are dark spots painted on the lower fuselage of some fighter aircraft, simulating a real cockpit canopy. The idea is that in a short-lived air battle, the enemy will make a split-second mistake in determining which direction the plane is facing and lose valuable time aiming. Night schemes, almost black or dark gray coatings for aircraft operating primarily at night, minimize the silhouette against the background of a starry sky or in moonlight. But there is an important nuance. In modern warfare, visual detection is far from the main threat. Radar, infrared sensors, and electronic reconnaissance detect the aircraft long before it can be seen with the eye. Therefore, camouflage today is more of a tactical addition rather than primary protection. Particular value remains in maneuverable close combat and low-level visual contact where the pilot's eye is still a valuable sensor. Different schemes are different answers to the question, who is looking at me and from where? There is no universal camouflage because there is no single threat. The pilot ejected over enemy territory. From this moment on, one of the most complex and risky types of military operations is launched: combat search and rescue. Combat search and rescue. The first thing that happens is the activation of the emergency radio beacon. A modern pilot's life jacket contains a small transmitter that is automatically activated when the parachute opens or comes into contact with water. The signal is transmitted at a certain frequency and can be encrypted so that the enemy cannot intercept it and ambush it at the site of the intended rescue. The second is identity verification. Before sending a rescue team, you need to make sure that the signal is actually being sent by your own pilot, and not by the enemy who has set a trap with a captured transmitter. To do this, a system of code words and personal identification data is used, known only to the pilot and known in advance to the rescue service, the so-called isolation Topher-line procedures. Third, the rescue operation itself. It usually includes several elements at the same time. Specialized helicopters, such as the HH-60 Pave Hawk, are equipped with additional armor and in-flight refueling systems to increase their range. Cover fighters that clear airspace and suppress possible ground threats. Electronic warfare aircraft to suppress enemy communications and air defense systems in the rescue area. Often, special forces, which land to directly cover the pilot until the helicopter arrives. The entire operation must be carried out as quickly as possible. Statistics show that the longer a downed pilot remains on enemy territory, the lower the chances of a successful rescue and the higher the risk of capture. One of the most famous operations of this kind is the rescue of Captain Scott O'Grady, who was shot down over Bosnia in 1995. He spent 6 days alone in hostile territory, subsisting on insects and rainwater, before a Marine rescue team successfully evacuated him under fire. The system for rescuing a downed pilot is an unspoken contract between the Army and everyone who sits in the cockpit of a combat aircraft. Promise, if you fall, we will come for you. This promise costs a lot of money, a huge risk for rescuers. But it is precisely this that maintains the morale of pilots who fly every day into areas from which they may not return. While ordinary people sleep, planes fly over international waters and along the borders of dozens of countries, which are rarely mentioned in the news. Their task is not to fight. And watch, listen, and remember. This is strategic aerial reconnaissance. And one of its most famous instruments is the RS-135 rivet joint aircraft. Externally, this is an ordinary passenger Boeing 707 3rd Series. But inside it's a completely different plane. Dozens of antennas protrude from the fuselage at different angles. Each is configured to receive a certain range of electromagnetic radiation. Rivet joint's mission is signal reconnaissance, SIGINT. The aircraft intercepts radio communications, radar operation, and signals from enemy communications systems. The crew specialists in signal analysis sit inside at computers, listening and recording everything the enemy emits in the electromagnetic spectrum. Why is this necessary? Every radar, every walkie-talkie, every communication system has a unique signature, frequency, modulation, characteristic features of the signal. By compiling a database of these signatures, analysts can accurately determine which air defense system is deployed in a particular area, where command posts are located, and even, based on the nature of the negotiations, whether a military operation is planned. Another tool is the RQ-4 Global Hawk drone. It flies at an altitude of about 18,000 meters, beyond the range of most air defense systems, and can stay in the air for more than 30 hours at a time. Its synthetic aperture radar is capable of creating detailed images of terrain through clouds, day and night, hundreds of kilometers away. There are also completely closed programs, reconnaissance satellites, high-altitude aircraft like U-2, which are still flying, although the first flight took place back in 1955. This entire intelligence system operates continuously, around the clock, all over the world. She rarely makes headlines. But it is precisely this that forms the picture of the world on the basis of which decisions are made on the deployment of forces, on negotiations, on war games. The war of the 21st century does not begin with the first shot. It starts with the first intercepted signal. The EF-35 program began in 1992 as a research concept. The first production aircraft entered service in 2015. More than 20 years from idea to combat use. Why is it taking so long? The first reason is the complexity of the requirements. The EF-35 was originally designed in 3 versions for 3 different branches of the military. Option A for the Air Force is normal takeoff and landing. Option B for the Marine Corps, short takeoff and vertical landing, for use from landing ships. Option C for carrier aircraft, reinforced landing gear and folding wings. Each option has different design requirements. But at the same time, customers wanted maximum unification of parts between options to save on production. This creates a colossal engineering challenge to design one basic airframe that can be adapted to 3 fundamentally different methods of takeoff and landing. The second reason is software. A modern fighter is a flying computer. The EF-35 contains more than 8 million lines of code on board, and even more in its ground support systems. For comparison, F-22 had about 1.5 million lines. Every line of code must be tested, certified, integrated with hundreds of other systems. The third reason is the detection of problems at later stages. Complex systems tend to reveal unexpected defects just when they are most difficult to fix. The EF-35 had many such stories: problems with the pilot's helmet cooling system, cracks in the airframe structure during fatigue tests, software failures in the weapons control system. Each such problem requires design revision and retesting. The fourth reason is political and budgetary. Military programs of this magnitude are financed from the state budget, which is reviewed annually. Changes in priorities, budget cuts, political pressure, all of this can slow down or speed up development, regardless of purely technical factors. The cost of the entire EF-35 program, according to various estimates, exceeds $1.5 trillion over its entire life cycle, including production, operation and maintenance for decades to come. This is the most expensive military program in human history. Long development is not a sign of incompetence. This is the price of creating a system that must work flawlessly in an environment where mistakes cost lives. For a long time, in-flight refueling was the prerogative of manned aircraft. But with the growing role of drones, the question arose: is it possible to refuel a drone in the air without a pilot on board? This turned out to be more difficult than it seems. Refueling a manned aircraft requires exquisite coordination between two crews, the pilot of the receiving aircraft and the boom operator on the tanker. The human brain constantly makes micro-adjustments, compensating for turbulence, gusts of wind, and the slightest deviations. The drone is controlled remotely, with a delay in the signal, and cannot respond as quickly and sensitively. The U.S. Navy solved this problem with the MQ-25 Stingray drone. Its initial task is precisely to refuel other drones and manned aircraft in the air, extending the range of carrier-based aircraft. Technically, this is solved by automating the approach process. The tanker drone and the recipient drone exchange precise data about their position through a secure communication channel in real time, an order of magnitude more accurate than conventional GPS navigation. Special algorithms calculate the approach trajectory, taking into account wind speed, turbulence from a neighboring aircraft, and other factors. The final docking phase is the most difficult. It uses a computer vision system. The cameras on both devices track each other's relative position with an accuracy of centimeters, and the control algorithm makes adjustments dozens of times per second, much faster than a person is capable of. Tests have shown that automatic refueling can be even more accurate than manual refueling because the algorithm does not get tired and is not susceptible to human factors that affect concentration after a long flight. Why is this even necessary? Autonomous refueling means that reconnaissance and attack drones will be able to remain in the air for virtually unlimited time. The only limitation remains the mechanical life of the airframe and engine, and not the fuel supply. This changes the very concept of air presence. Instead of sending a new aircraft to replace a tired one, you can keep the same aircraft in the air for days, refueling it with other drones that also do not get tired. The turbojet and turbofan engine ruled the skies for over 70 years. But military engineers are already working on a fundamentally new generation of power plants. And the reason is simple: modern requirements for fighter aircraft go beyond what existing technologies can provide. One of the main projects is an adaptive engine with a variable operating cycle, the Advent program, and its continuation, ATP, Adaptive Engine Transition Program. The problem this technology solves goes like this. The engine with a high bypass ratio is efficient in cruising mode, economical, provides a long range. But it is poorly suited for maximum thrust in maneuverable combat. An engine with a low bypass ratio, on the contrary, provides excellent thrust for combat, but is gluttonous in cruising mode. Previously, you had to choose one thing when designing an aircraft. The adaptive engine changes the airflow ratio in flight. A special electronically controlled third air circuit allows the engine to switch between economy mode and maximum power mode on the fly. The result is, according to calculations, an increase in flight range by 25 to 30% while maintaining maximum combat thrust. For a sixth-generation fighter, this means the ability to carry out missions at a significantly greater distance from the base without sacrificing maneuverability in combat. The second direction is hybrid electric power plants. While this sounds futuristic for combat aviation, research is already underway. The electrical component can provide power for powerful onboard systems, laser weapons, next-generation radars, electronic warfare systems, without the need to draw power directly from the main engine at a critical moment. The third direction, much more distant, is detonation engines. Instead of conventional fuel combustion, which occurs relatively slowly, a detonation engine uses a shock wave to release energy more efficiently and powerfully. Theoretically, this could provide a significant increase in efficiency, but the technology is still far from practical combat use. There are too many unresolved engineering problems with materials capable of withstanding such extreme conditions. The engine is the heart of any aircraft. And each next generation of combat aviation will be determined not so much by the shape of the airframe, but by what happens inside this heart. It is here that some of the most secret and expensive research in the world of military aviation is concentrated today. The fourth part. 40 blocks in total. 40 different angles on the same topic. Military aviation is the embodiment of human ingenuity in the face of physical limitations. Every detail we disassembled, from the shape of the air intake to the drone's refueling algorithm, is the result of thousands of hours of engineering work, testing, errors, and their corrections. Technologies do not stand still. And somewhere right now, engineers are solving a problem, the answer to which will be the topic of one of the future videos.